Good morning or afternoon. My name is Sang-Gon and I'm an undergraduate student from the Department of Computer Science at Kookmin University. It's an honor to be here and to have an opportunity to present my research in this session. Today, I will brief you on my research progress on bias and hate speech detection using BERT-based pre-training model. What information on hate speech are you aware of? Hate speech indicates hateful expressions which attack a person or group by their gender, race, etc. Malicious comments on hate speech and gender bias have been abusing online communities, and they are causing social problems in our society. Recently, to solve the problem, a method of classifying malicious comments has been studied. In 2017, one study released 3 datasets consisting of hate speech, gender bias, and gender bias in public so others can evaluate their model. In this research, we trained our transformer-based model with multiple pre-trained models using strategies to improve performance, and finally, we evaluated our model in the 3 Kaggle competitions. We used a dataset labeled with 3 different types of tags for training. The dataset has consisted of a train set, a depth set, and a test set. The test set is an unlabeled dataset. In case of Korean gender bias, it is binary classification problem. Another 2 datasets, Korean bias and Korean hate speech, are multi-class classification problem. As shown in the figure in this slide, the dataset is extremely unlabeled. Since it may cause poor performance, we implemented a data sampling strategy which will be explained the detail in the following slides. This slide outlines the structure of our classification model, which uses a BERT-based pre-trained model. The classification is performed using the BERT embedding vector of the CLS token by taking it as the input vector of the FC layers. For hyperparameter tuning, we tested for 1 layer and 2 layers of FC layers, and different values of dropout rate, loading rate, and batch sizes. In the case of 2 layers of FC layers, a hidden layer is set to output a 1024 dimensional vector, and dropout regulation was applied to the corresponding hidden layer. Finally, we used RMW optimizer with Walmart linear scheduler for learning rate and used cross entropy loss function. In order to proceed with transformer-based deep learning models, pre-trained language models including BERT, Roberta, and Electra are used as base models. The table shows the pre-trained models that have been trained for each model. Specifically, we used 4 different pre-trained models. First, Cobalt is a BERT-based model built by SKT. And second, Sungju BERT is a Roberta-based model built at Sungju University. And third, Clue Roberta is also Roberta-based model built for the Korean language understanding evaluation platform. And lastly, KC Electra, which stands for Korean Comments Electra, is a Electra-based model. You can notice that BERT Sungju and KC Electra are pre-trained using a corpus reflecting real-world characteristics. We used 4 major strategies to improve the performance of our model. Here is the first strategy. As I mentioned in an earlier slide, the dataset for training is extremely unbalanced. So we implemented a data sampling strategy with oversampling. In a situation where the size of the train set is small, reducing the number of data deteriorates the model's performance. So we used oversampling instead of undersampling to avoid a reduction in the number of data since the size of the train set is already small. The dataset was constructed through random shuffling by simply amplifying the data of the smaller size by n times. The second strategy is logic ensemble. It is known that since the pre-training models were trained based on a different corpus, performance can be varied on task even with the same dataset for training. To maximize the benefit that having multi pre-trained models, a logic ensemble was implemented as the equation shown in this slide. We tried to improve the performance by performing logic ensemble to find the weight lambda that shows the maximum performance for the validation set. The third strategy is ensemble based on label distribution. It's possible since the different types of labels are labeled on the same dataset. Therefore, we can get a statistical correlation between different labels, which means using this correlation, we can ensemble models that perform different classification tasks. For example, if a bias detection result is not none, the weight of the none prediction in the hate speech detection is lowered. That is, weighting scheme for the ensemble is conducted by conditionally using the bias detection result, which has better performance than the hate speech detection. Lastly, XGBoost was tried to improve performance. XGBoost, which stands for Extreme Gradient Boosting, is one of the ensemble techniques that makes a strong prediction by combining several weak decision trees. We used the last hidden state output value of the BERT-based model to train the XGBoost model after the BERT model was fine-tuned with an MLP head. We experimented with all three tasks, which are gender bias, general bias, and hate speech detection. In gender bias detection, the Orta pre-training model from Sungji University showed the best performance in the single model while recording F1 score of 0.74. And using the logic ensemble, we achieved the highest performance as shown in the table by recording F1 score of 0.77, which is higher than the baseline 0.68. In general bias detection, the KC Electra pre-training model showed the best performance in the single model by recording F1 score of 0.69. And using the logic ensemble and ensemble by label distribution, we achieved the highest performance as shown in the table by recording F1 score of 0.716, which is higher than the baseline 0.63. For the ensemble by label distribution, we used our best model from Korean gender bias detection, since the gender bias problem contains gender bias problem. In hate speech detection, the KC Electra pre-trained model showed the best performance in the single model by recording F1 score of 0.64. And using the logic ensemble and ensemble by label distribution, we achieved the highest performance as shown in the table by recording F1 score of 0.65, which is higher than the baseline 0.52. For the ensemble by label distribution, we used our best model from Korean gender bias detection, since the gender bias problem and hate speech problem have a correlation on label distribution. Although we tried to improve performance by applying XG boost, it showed the lower performance than the single model. These are screenshots of all three Kaggle competition leaderboards as of March 15, 2022. As you can see here, gender bias and general bias problems ranked first and hate speech detection ranked third, achieving the highest level of performance. I'd like to sum up my presentation with the following conclusions. We explored a bias and hate speech detection problem by applying 4 pre-training models of transformer-based deep learning models. The results show that pre-trained models of using a corpus reflecting real-world characteristics at pre-training, such as BERT-based and KC-Electra, are well performing in the gender bias and hate speech detection. Moreover, we achieved the best performance using an ensemble strategy with the label distribution. Finally, by participating in the Kaggle competition, we showed that our model achieved the highest level of performance. Thank you for listening.